Hello there, universe explorers! Ready to unravel some of the greatest mysteries of our cosmos? Today, we're embarking on a journey that will stretch your imagination to the farthest corners of our universe and challenge what you thought you knew about its birth and evolution. We'll delve into theories that boggle the mind, evidence that leaves us awestruck, and concepts so profound they can change the way we see our place in the cosmos. Hi Ed lovers, Jay here, and welcome to EdPOP, your go-to channel for the best science facts and curiosities you can't find anywhere else. But before we get started, be sure to subscribe and turn on notifications so you never miss a new video. We have a lot of fun here, diving into topics that are as vast as the universe itself, and we want you to be a part of it. Today, we're venturing into an exciting realm of cosmic exploration, diving into theories that have been at the forefront of scientific thought and contemplating the implications they hold for our future. As we journey together, we'll be asking questions, making connections, and learning more about the fascinating, intricate universe we call home. We'll challenge the boundaries of our understanding, open our minds to new possibilities, and revel in the awe-inspiring beauty of our cosmos. Remember, our goal here is not just to learn, but to ignite a passion for exploration and discovery. So, grab your space helmets, Ed lovers, and let's embark on this cosmic adventure together. Did you know that cosmic inflation is the theory of a rapid, exponential expansion of the universe shortly after the Big Bang? In the great cosmic narrative of the birth and evolution of our universe, cosmic inflation takes center stage during the very early epochs. Picture this: less than a trillionth of a second after the Big Bang, the universe, smaller than an atom, starts expanding exponentially. It doubles in size, again and again, ballooning out to about the size of a grapefruit in the blink of an eye. Now, this isn't just regular expansion, it's expansion at a speed faster than light, defying the ordinary rules of cosmic speed limits. This theory was proposed by physicist Alan Guth in the late 20th century. He was trying to solve certain problems with the Big Bang theory when he realized that a super-fast expansion could explain away these issues. This idea, born out of quantum physics, posits that in the high-energy environment of the early universe, a type of energy field could lead to an immense anti-gravitational push, causing the universe to inflate rapidly. Since then, the theory of cosmic inflation has become a cornerstone of our understanding of the universe's origins. It provides a context for the Big Bang, painting a picture of the extraordinary events that took place in the fleeting moments after our universe's birth. Did you know that the cosmic microwave background, CMB, provides evidence for cosmic inflation? Have you ever wondered what baby pictures of the universe might look like? Well, we have something close: the cosmic microwave background, or CMB. It's a snapshot of the universe about 380,000 years after the Big Bang, and it's the oldest light that we can detect. When it was first discovered by accident in the mid-20th century by Arno Penzias and Robert Wilson, it confirmed the Big Bang theory, and it's been a treasure trove of information ever since. But how does this ancient glow from the early universe provide evidence for cosmic inflation? The CMB is remarkably uniform in temperature across the sky, with only tiny fluctuations. This uniformity is exactly what we'd expect to see if cosmic inflation had happened, smoothing out the universe to an almost perfect uniformity. In addition, the specific patterns of these tiny temperature fluctuations match predictions made by the theory of inflation. These patterns, seen as tiny speckles in images of the CMB, are imprints left by quantum fluctuations in the early universe that were stretched out by cosmic inflation, providing the seeds for the galaxies we see today. Did you know that inflation solves the flatness problem and the horizon problem? Before the theory of cosmic inflation was proposed, there were some major issues that puzzled cosmologists about the Big Bang theory. Two of these are the flatness problem and the horizon problem. The flatness problem is about the geometry of our universe. You see, it's remarkably flat, and by that, we mean the large-scale curvature of the universe. Now, this might not sound strange, but given the possible conditions at the time of the Big Bang, this is highly unexpected. Then there's the horizon problem. You've probably noticed that no matter which direction you look in the night sky, the universe looks pretty much the same. Now, this might seem natural, but given that the universe has a finite age, this uniformity is odd. Different regions of the universe should not have had enough time to communicate with each other and sync up their temperatures. Hey, wait! Now's the time! Subscribe to the channel to be entertained while learning. It's free! This is where cosmic inflation comes in, providing an elegant solution to these problems. If the universe underwent a rapid expansion in its infancy, it could have smoothed out to an almost perfectly flat state, solving the flatness problem. And if regions of the universe were in close contact before inflation, they could have reached the same temperature and then got moved apart by inflation, explaining the uniformity we see today. Did you know that the theory of cosmic inflation leads to the concept of a multiverse? Okay, fasten your seatbelts, because things are about to get even weirder. You see, if cosmic inflation happened once, it could happen again, and again, and again. In fact, it could happen countless times in different regions of space. This leads to an astonishing implication: the existence of a multiverse. Imagine our universe as just one bubble in an endlessly frothy cosmic ocean, with each bubble being its own universe with its own laws of physics and properties. Now, this isn't the only type of multiverse that physicists and cosmologists talk about, but it's the one that's a direct implication of cosmic inflation. This idea, while mind-bending, opens up new avenues for exploration. However, it also raises difficult questions. For instance, if there are other universes with different laws of physics, can we ever detect them? And how can we test the validity of the multiverse concept if we can't observe these other universes? Did you know that cosmic inflation implies the fundamental constants of physics could vary in different universes? Different universes in the multiverse could have different physical properties. If this is the case, the so-called constants of nature that we're familiar with in our universe might not be so constant across the multiverse. The strength of gravity, the speed of light, the masses of elementary particles. These could all take different values in different universes. This has deep implications for our understanding of the universe. For example, some physicists have suggested that the reason the physical constants in our universe seem so finely tuned for the emergence of life is that we're simply in one of the many universes where these conditions allow life to exist. This idea, known as the anthropic principle, is quite controversial, but it's an interesting perspective that emerges from the possible existence of a multiverse. However, we should note that these are highly speculative ideas. While they're fascinating to consider, they're currently beyond the reach of experimental verification. But who knows what the future might hold? Did you know that the theory of cosmic inflation is not universally accepted and still faces challenges? Despite its successes, cosmic inflation is not without its critics. While it's a beautiful theory that solves many problems, some physicists have raised concerns. For instance, they argue that the theory relies on some assumptions about the early universe that are not backed by empirical evidence. Others feel uncomfortable with the theory's implications, such as the multiverse, which they see as untestable and hence not scientific. It's also important to understand that cosmic inflation is not the only game in town. There are other theories that aim to explain the same observations, like the cyclic model, which proposes that the universe goes through endless cycles of expansion and contraction, or the theory of quantum gravity, which aims to reconcile quantum mechanics and general relativity and might give us a new perspective on the early universe. Remember, science is a self-correcting process. Theories are meant to be tested and challenged. In fact, it's through these challenges and debates that we make progress. So, the story of cosmic inflation is far from over. Did you know that our understanding of cosmic inflation could drastically change our future in space exploration and theoretical physics? As we refine our understanding of cosmic inflation and the early universe, this could have profound implications for the future. It could reshape our perspective on space exploration and our attempts to understand the fundamental laws of nature. Imagine if we could detect signatures of other universes in the cosmic microwave background, or if we could probe the quantum nature of space and time to get a better handle on the early universe. These might sound like science fiction, but they're exactly the kind of things that could be possible if our understanding of cosmic inflation is on the right track. Of course, these are grand challenges, and there's a long road ahead. We won't know where this journey will take us, but one thing's for sure: the future of cosmology and physics is going to be exciting. From tackling the mysteries of dark matter and dark energy, to exploring the potential existence of other universes, to to trying to understand the nature of time itself. There are plenty of adventures ahead on our cosmic journey. Thank you so much for embarking on this cosmic journey with us. If you enjoyed the video, don't forget to hit that like button, share it with your fellow universe explorers, and subscribe for more awe-inspiring journeys into the world of science. We can't wait to explore more scientific mysteries with you. Remember, there's always more to learn, and the universe is full of surprises.